So I think we can start. I'm Evan Welbourne. I lead machine learning for Alexa Smart Home. And I'm fortunate to be joined by two of our leading machine learning engineers, Akshay Kumar and Dylan Rush. They're going to be showing a demo shortly. And for those of you who have been following Alexa at Remars or just in the news, you're probably familiar with our use of machine learning for the spoken language interface. And what we're going to show you today is a little bit different. We're focusing specifically on how, in conjunction with spoken language understanding, we can use sensed context and behavioral patterns in the Internet of Things to help our customers. So for smart home, this means that we can build models that help make smart homes simpler to use for customers and more convenient. And we also find ways to help customers keep their homes and their property safe. So high-level roadmap of what we're going to talk about in this session. We're going to start with sort of what it is to build a smart home, a brief history of smart home technology, starting all the way back in the 80s and coming to today, both as a way to kind of articulate classic pain points in smart home and also the challenges that we face today with a much broader, more diverse base of customers. And then second, we're going to jump into the demo. Akshay and Dylan are going to walk us through several of the smart home machine learning features that we launched in the last year, including Did You Mean, Alexa Hunches, and the Away Lighting feature of Alexa Guard. And then following the demo, we're going to jump into the machine learning that we use for each of these features. And at least at kind of a high intuitive level, we're going to show kind of end-to-end how each of these features works, the kinds of modeling that's involved, and the data that are used. So starting with the feature about simplicity, Did You Mean, then talking about Alexa Hunches, which is more about convenience, and then going into Alexa Guard, which is really more about safety and security. And then we'll wrap up with some closing remarks and a look towards where we're going in the future. Okay, so building a smarter home. So smart home technology, not everyone is familiar with the history of smart home, but it's actually a pretty long history. It goes back decades. So even back in the 80s, people were working on home automation. It was very much the domain of the DIYers, really tech-savvy, do-it-yourself folks at home, using technologies like X10, wiring things up, connecting devices through your electrical system at home. And for that reason, it was pretty hard to do. It was pretty expensive, and there were limited devices you could use, and there were limited customers for a smart home. And it stayed that way for really a couple decades. And there were certain incremental advances on technology, but we didn't really see any major changes until the sort of advent of smartphones. And with smartphones, we saw this new capability, which was to have this one device which became sort of the universal remote control for your home. Just gonna move this back a little bit. And yet it was still pretty clunky, right? You had to take your phone out of your pocket, unlock it, navigate to the app that was to control your home, open the app, navigate to the device that you wanted to switch on, and then if it was connected, you click it, and then your light turns on, right? So it was not much more convenient than actually going to the wall and flipping on the switch. And at the same time, these apps tended to create walled gardens. There was only a limited selection of devices that would work with any given app. So there were still few customers, limited selection of devices, limited adoption. And then flashing forward to nowadays, just 5 years ago, we announced Alexa. And soon after, we found customers writing their own custom smart home skills. They were writing skills that allowed them to use their voice to control their smart lights or whatever smart devices they had in their house. So as always, we listened to our customers. We ended up building some smart home capabilities into Alexa. And what we found is that this voice-first experience for smart home was really the great enabler. So this enabled many more people to get into and use smart home. It was much lower friction for the customer to just turn on a light. You could just say, Alexa, turn on the light, and the light turns on. You don't have to navigate an app or unlock anything. Setup was easier. You can do setup through voice or through the app, however you want. And then, in addition, we made it much easier for device manufacturers and developers to connect any new device to Alexa. And for that reason, we have a lot more devices connecting with Alexa these days. And so there's much more selection for customers that want to build their own smart home. And so all of these things taken together have really resulted in, for the first time in really decades, smart home starting to go more mainstream, right? So a few stats about that. From Amazon.com, we know that there have been over 100 million Alexa-enabled devices purchased, so 100 million devices. And these are all kinds of devices, right? So all of the devices we think of as classic smart home devices like lights, plugs, locks, switches, security systems, televisions, cameras, all these things are certainly included in that count. But there's the long tail of all kinds of other devices as well, right? So there's essential oil diffusers, baby monitors, automated pet food dispensers. There's all kinds of devices that work with Alexa. And as of today, there are 60,000 Alexa-compatible devices. And then we also have this program that's called Works with Alexa for devices that meet our particularly high bar for reliability, functionality, and compatibility. And if a device meets that high bar, it becomes Alexa certified, Works with Alexa certified, and then they get a badge on Amazon.com. And we have already 8,000 devices that meet that very high bar for customers. And then this growth in devices and customers is not just limited to the US, it's global. We have smart home supported in English in 80 countries, and there's locale-specific support in 15 more countries. So if Alexa needs to speak another language, she can do that. Just last year, we launched in Spain, Italy, Japan, India, and French-speaking Canada. And that international expansion is also something that's continuing. Okay, so with this explosion in devices and customers and so on, one of the important points for a talk about machine learning is that we're seeing a much more diverse customer base. There's much more diverse use cases, and we see customers kind of falling into several demographics. There's, of course, the early adopters. These are the traditional smart home customers. They're tech savvy. They're DIY types. They're going to buy smart devices one way or another. So they remain smart home customers, which is great. We love the early adopters. But there's another segment. There's a newer segment of customers, which we refer to as smart home curious. And these are the folks that are accepting of new technologies. They're interested in smart home, but it really has to save them time and be very convenient for them. And they're willing to learn, but it can't be too hard. It can't be too technical, or it's kind of not worth their time. So this is sort of a new demographic we look at, and that is especially important to support with machine learning features. And then there's a third demographic, which we refer to as security-driven. And these folks are primarily interested in new smart home technology as a way to secure their home and to protect their family and their property. So the challenge is really, how do we support the diversity of customers across these demographics, across countries, across sort of combinations of devices? There's lots of new problems coming up. And in particular, we're focusing on applying machine learning with sort of three main goals, right? So one goal is to increase the simplicity of interaction with devices in the smart home. It should be very easy for customers to interact with devices in their home. They can use whatever language they like and effectively control their home. And then the second is convenience. So the smart home should be responsive to the customer's typical behaviors. It should do things automatically whenever it's appropriate. And then the third is safety, right? So smart homes should be able to help customers keep their homes safe. So to concretely illustrate how we're approaching this problem with machine learning, we're going to demo several features that we launched in the last year. And for the purposes of the demo, we've got this smart home curious customer we're calling Jay. So Jay is smart home curious. He lives in Las Vegas. He's had Alexa for about 6 months. He's used Alexa primarily for listening to music or getting the weather, the news, things like that. But he's just getting into smart home. He's interested in smart home. So this demo essentially traces Jay's journey as a new smart home customer in his first month, and we'll see how Alexa uses machine learning to help make the smart home experience simpler, more convenient, and also helps him protect his home. So I'll hand it over to Akshay to start the demo.
Hello. Perfect. Thanks, Evan. So my name is Akshay, and I'm a machine learning engineer in the Smart Home ML team. And the first feature that we're going to demo for you today is called Did You Mean, or DYM. DYM aims to make the smart home simpler for the customer by allowing them to control their smart home in a more natural way. So even if a customer like Jay makes imprecise control directives to the smart home, Alexa will be able to understand what they're trying to do. Let's take Jay for an example. Jay is a smart home curious customer, and he's by no means a power user. He has set up a smart home, and as you can see, he has a bedroom light, which is this little lamp on his nightstand. He has this little couch or big couch light in his living room, and he has a desk fan in his office, which is this guy. So Jay wants to control his smart home in a natural way. So to illustrate that, let's take a look at the first day in the first week in the life of Jay's smart home. Let's say Jay wakes up at 7 a.m. in the morning in his bedroom. He's a little groggy in his sleep, so he wants to turn on his bedroom light. So he says, Alexa, turn on master.
Did you mean bedroom light?
Yes.
Okay.
Perfect. What we saw here is an example of Alexa's capability to infer location-to-location similarity. She understands that within the context of smart home, the word master is closest in relation to the location of bedroom, and is thus correctly able to infer that by master, Jay probably meant to control his bedroom light. Let's fast forward a little bit through his day. He gets up, gets ready, goes to work, and later in the day, he comes back home, and to relax and wind down, he wants to sit on his couch and watch some TV. At this point, he wants to turn on his couch light, which is this guy, and he says, Alexa, turn on sofa lamp.
Did you mean couch light?
Yes.
Okay.
Great. So that was an example of Alexa's capability to infer object-to-object semantic similarity between the word sofa lamp, or the phrase sofa lamp, and the name he has given to his device called couch light. After watching some TV, Jay wants to get some work done in his office, so he goes up to his office. It's a little hot, so he wants to turn on his desk fan. At this point, however, Jay does not remember the exact name that he has given to his fan, but he does remember the brand to which the fan belongs, which is Dyson in this case. So he says, Alexa, turn on Dyson.
Did you mean desk fan?
Yes.
Okay.
Perfect. So that was an example of Alexa being able to leverage the name of a brand and form a relationship between the brand name and typically the devices that that brand produces. She understands that Dyson is a common manufacturer of fans and thus infers that by Dyson, Jay probably meant to control his desk fan. So that concludes Jay's first day of smart home usage through Alexa. In addition to using Alexa to control his smart home, Jay also has a habit of settling in his bed for about an hour or so before he goes to sleep in order to read. He has this bedroom light, which he calls it, on his nightstand, which he usually uses to read. Let's put a pin in that because we'll come back to it in week 2. So Jay repeats this sort of similar pattern of usage of his smart home for the first week, and now we'll move on to week 2. All right, I'm going to reset all these devices just to kind of simulate the passage of time. All right, perfect. So, in addition to making the smart home simpler for someone like Jay, DYM also makes it simpler to use smart home for a household with multiple people. Let's say in week 2, Jay's mother is visiting him from India. Jay is extremely excited about his smart home configuration, and he gives her a brief overview of how Alexa works and how the smart home configuration works before heading off to work. Alone at home at this point, Jay's mother decides to make a call back to India to explain how she's arrived all safe and sound at Jay's place. In order to do that, she wants to go to the office. She goes to the office, again it's a little warm, and she wants to turn on the desk fan. Not being the person who set up the smart home, she does not exactly remember what the desk fan is really called. So she says, Alexa, turn on office air.
Did you mean desk fan?
Yes.
Okay.
Great. So what we see here are a couple of things. The first thing being Alexa's capability to infer a location to object similarity, where she understands that the word office, which in this case is the place, is the closest in relation to the object of the desk. And the second, she understands the relationship between a device, which in this case is the fan, and its utility, which is the production of air. Let's go back to Jay. If you remember from the first week, we talked about Jay's habit of settling in his bed for a session of reading for about an hour. Let's say Jay is sitting on his bed again and he wants to read. However, he's a little far away from the switch that he usually uses to control his bedroom light. So he says to Alexa, Alexa, turn on reading light.
Did you mean bedroom light?
Yes.
Okay.
What we see here is an illustration of Did You Mean's capability to leverage personalized contextual signals in order to make the smart home simpler for Jay. She understands that usually before going to bed, for about an hour or so, Jay uses his bedroom light for reading. And because of that, she's able to form a relationship between the activity of reading and the device called bedroom light. With that, I will conclude the demonstration of Did You Mean and hand it off to Dylan, who's going to walk us through some of the other machine learning features for smart home.
Thanks, Akshay. So far we've seen how Did You Mean can allow a smart home customer to interact with their home in a simpler way through these imprecise directives. So let's look at ways that Alexa can make a smart home even smarter. So Jay wakes up in the morning and he noticed that he left his reading light on. I guess he's a very heavy sleeper. And so he says, Alexa, turn off reading light.
Did you mean bedroom light?
Yes.
Okay. By the way, your desk fan is on. Do you want me to turn it off?
Yes.
Okay.
So here we could see that Jay has established a behavior of normally keeping his desk fan off during the week or during the daytime. And Alexa has picked up on this, and she's determined with high confidence that this desk fan actually shouldn't be on in the morning. So she's made the suggestion to Jay to turn the desk fan off, making it a little more convenient to manage his house, saving a little bit of energy. So let's move on to week 4. Okay, so it's week 4. Jay has been using these devices for a little while. His mother has insisted that he gets a security system to make his home a little more secure. So Jay goes out and he purchases this smart lock here and installs it on his front door. He uses it for a few days, establishing a pattern of locking his door in the morning when he goes to work and locking his door in the evening when he goes to bed. So now, one evening, Jay is going to sleep. He says, Alexa, set an alarm for 7 a.m.
Alarm set for 7 a.m. tomorrow. By the way, your front door is unlocked. Do you want me to lock it?
Yes.
Locking. Hang on. The front door is locked.
So here's another example where Alexa is kind of proactively managing Jay's home on his behalf. So she's picked up on this pattern of when he normally keeps his door locked, and she's made this suggestion to Jay to help him keep his home safer. So now there's one more feature that I'd like to mention. You can enable Alexa Guard on your account. And if you own an Echo at home, Alexa Guard can listen for break-ins, listen for fire alarms or burglar alarms, and she'll notify you if there's some kind of intrusion or some kind of issue with your house. Another feature alongside that I'd like to highlight is away lighting. So Jay, as a smart home customer, because he owns some lights, he's actually able to enable this away lighting feature. So here's an example. This is a time-lapse video of a customer with smart lights enabled. So using away lighting, this customer is able to make it look like they're home when they're actually away. So based on the names of the devices and the inferred locations in the customer's house, it actually kind of looks like somebody's home. Wrapping this up, so far we've seen simplicity by these imprecise directives. We've seen the convenience of allowing Alexa to manage your home on your behalf. And Alexa is also making it easier to help Jay keep a secure home, both through these lock hunches and through this away lighting feature. So with that, Evan?
Okay, all right, thank you. So we've seen the demo, we've seen some of these features in action in kind of this mock scenario. Now we're going to talk about how machine learning is used to empower customers through these features. So the first feature we're going to talk about is this Did You Mean feature, which Akshay demoed. We also call it DYM. So DYM is about simplicity, right? So customers should be able to refer to their devices using whatever sort of natural expression that they would like to. They don't need to use exactly the phrase that the customer who set up the device used when they named the device. It could be that they set it up and forgot it, or it could be that someone else in the household set it up and they just don't know what they named the lamp or the red lamp or whatever it's called. So Did You Mean is set to help with that. And it's worth noting that from a machine learning perspective, it's not entirely dissimilar from what you see in search engines. When you have a typo in your query string, the search engine often will come back to you and say, oh, did you actually mean this different string, slightly different string? And then you click that, and then you get the results page that you wanted to see. So it's similar, but there's some important distinctions. One is that what search engines do is typically just looking at kind of word distance, sort of syntactic similarity. So that's important. Did You Mean does that, but more important for Did You Mean is semantic similarity. So as Akshay demonstrated, there's the similarity between master bedroom or sort of master and bedroom. Like there's a similarity there between those words that's important. And then more importantly is that semantic similarity is just not sort of like an English thesaurus. It's specific to the smart home space. So master and bedroom are similar, and also the words family and living are similar. They're not similar in English, but because family room and living room kind of mean the same thing, they end up being close to each other in a smart home sense. The other note about the difference with Did You Mean, as Akshay also showed us, is that we use the behavioral patterns to kind of pull in some more information about what device the customer is probably targeting. So if you have this lamp in the corner and you've got a desk fan and a door lock, and it's 7 p.m., you always use this lamp for reading at 7 p.m. and you say turn on X, right? X doesn't contain any information about which device you're really speaking about, but the fact that you always are using that lamp at that time kind of tells us that that's probably what you're targeting, right? So Alexa uses that information as well as the semantic similarity to deliver the Did You Mean experience. So now we'll kind of look under the hood a little bit more of the machine learning, and we'll show you the Did You Mean flow in a nutshell. And the goal is not really to talk in exact detail about the models we use or the performance of those models or even the architecture of the system, but really to just convey sort of the intuition and the end-to-end flow of the reasoning and Did You Mean. So starting like in the demo with the imprecise customer utterance. It could be that they used a different name for a device they wanted to target, or that somehow it was sort of awkward phrasing, or in some cases there's even an ASR error that comes through. So we start with that imprecise utterance, and then the goal is really to get to the top K list of devices that the customer is likely to be targeting. So we produce a ranked list of devices, and we take that top one as what we think the customer is most likely to have said. So how do we do that? So let's look at the models and the data that are concerned with the Did You Mean experience. And to start, really the first concept we develop is like we were discussing, the concept of semantic similarity. And that depends on this data type that's called that we call it the device registry. And so a little more information on device registry. So here from the demo, this is the contents of Jay's device registry. You see this in your Alexa app on the All Devices page. This just contains really the metadata about the devices that are set up in your home, right? So for Jay, you can see that he's got the bedroom light, the couch light, the desk fan. These are all parts of the registry. It contains the names that the customer has set up the devices with, as well as the type of device. Is it a light? Is it a plug? And then there's some additional metadata like the manufacturer. Is it a TP-Link plug? Is it a Philips light? What have you. And then for those of you that are familiar with smart home, you might also be familiar with the concept of groups. So groups are this idea where if you have, for example, say 15 different smart lights and they're all in the recessed lighting in your kitchen, you probably don't want to control them individually, so you can create a group that is called kitchen lights and that allows you to control them together. So you can say turn on kitchen lights or turn off kitchen lights, and then it controls all the devices together. So that information is also part of this device registry. So it's essentially just your smart home setup contained in the registry. So using what the customer said and using the device registry, we build this model for semantic similarity. And so it may be no surprise for those of you with machine learning experience that we're using an embedding. And essentially, this is an embedding that captures the similarity between what customers say and the contents of the device registry. So all of the information about the name of the device, the brand, the type of device it is, all of that is in there. And it's a complex process to create an embedding, but just to give a sense of some of the data that we use, we look at corrections that customers make in their VUI experience. So in the example from the demo, Jay says, turn on the sofa light, and then it fails. And then maybe a few minutes later, Jay or a similar customer would say, turn on the couch light, and it succeeds. So that gives us a signal. It's a bit of a noisy signal, but it gives us a signal that maybe there's some similarity between what they tried and then what actually succeeded. So in this case, sofa lamp and couch lamp. And so on the right side is an illustration. It's not visualization, but just an illustration of this concept of an embedding. Should be familiar to those of you with experience with word embeddings, sentence level embeddings. Just showing that what comes out of this process is kind of a mapping from devices or things that the customer says to this space of sort of vectors that represent similar devices. So for example, you see here couch and sofa are close together. Things related to the kitchen tend to be close together in that embedding, and then it's similar for each area of the house and each type of function and so on. So that's a key concept, the semantic similarity. The other thing we talked about was behavioral modeling. So there's also a behavioral prediction that is part of the DigiMean experience. And this relies on several types of data. So first, there's voice interactions. So this is simply the history of the customer's interactions with Alexa. So Jay says, turn on the couch light, turn off the couch light, turn on the fan, so on. All of these are in the customer's history here shown in the app. And there's additional utterances there too. So for example, if Jay says, Alexa, good night, or he sets an alarm for the next morning, that gives us a little bit more context. It sort of signals that he may indeed be kind of signing off for the night. So that can be useful as well. So that's voice interaction. There's also device state. So with respect to device state, here visualized in the app as an example of device state, it is what it sounds like. In this case, the state displayed for the back porch light is that the light is on and the brightness is set to 100%. And also included in state are things like the color of the light or the temperature or so on. Whatever state is reflected by your device is captured in this device state. And so when we talk about device state changes, so when Jay says turn off the couch light state changes from on to off. So that's an example of a state change. And then lastly, of course, there's always some kind of environmental or situational data, right? Like what time of day is it? What day of the week is it? Is it a weekend or a weekday? What's the season? Is it light outside or is it dark outside? That's always important for lighting. So that data is included as well. So just to, again, kind of dig into the behavioral prediction, using that data, we kind of develop a sense of when a particular device is going to be on and when that device is probably going to be off, right? So the plot on the right is showing kind of one slice of a visualization about the pattern for a device. In this case, it's a light. On the x-axis, we see the hour of the day. And then on the y-axis is the probability that, in this case, a light is on. And so what you see is that, okay, at nighttime, it's likely that the device is on, and then during the day, the device is probably off, which is a typical kind of pattern for a light. And there's a confidence interval as well. So you can also break that out by day of the week, for example, to see a little more. You see this kind of pattern here. I can't point to both screens, but these lines kind of in the middle here are representing the weekend. And so again, intuitively, you can see that on the weekend, people are more likely to be using lights during the day versus on a weekday, the lights are typically off, right, because people are at work. So the behavioral prediction is another key piece. And now that we've sort of developed ideas of semantic similarity and behavioral prediction, we can talk about the ranking algorithm, right? So really, this is kind of the core of did you mean. So given semantic similarity and given a notion of behavioral prediction, what's the customer most likely to do next? We have this ranking algorithm that considers, weighs all of the evidence and tries to produce this top K list that accurately predicts what the customer meant to say, even if they didn't say it correctly. And so Alexa takes that top K list and then responds to the customer with an inquiry. Did you mean whatever that type of device is? And so the customer gives us feedback as well. So they will say yes or no to a did you mean? And then, of course, that's great ground truth feedback to the ranker and to every other part of the did you mean experience. So just a word about the impact of this feature. It's relatively new. We launched it just 6 months ago. And even in that time, it's had a pretty good impact for our customers. There's over 1 million did you means that have been sent. And in these scenarios, like we showed, which are very common in the demo, where the customer is referring to a device by some name other than the exact name in the device registry, or there's something awkward in the phrasing, the customers are actually accepting or saying yes to the did you mean more than 90% of the time, which is great. And using that feedback, Alexa is able to constantly improve and get smarter. So it's constantly improving as well. So great feature to help especially new customers with making smart homes simpler. So the next feature that we're going to talk about is Alexa Hunches, which Dylan demoed. And Hunches is more about convenience, right? So Hunches is really about Alexa learning the patterns and the sort of preferred states that you want your home to be in, right? So in the example, the hunches that Dylan showed were about Alexa kind of reasoning about the lock in Jay's house. So it looks like the lock is usually locked at night, but it seems like it's unlocked and it sounds like you're going to bed. Do you want me to lock the door? Right? There's sort of an intuition there about what should probably happen. Doesn't quite look right. So Alexa proactively reaches out with a hunch to Jay and asks him if he would like to lock the door. And then the other one was about the fan, right? So it looks like the fan is usually off during the day, but it's still on. That looks pretty unusual. Would you like me to turn the fan off? So that's another example of a hunch. So in a similar fashion, let's look at hunches and kind of build some intuition about how Alexa is reasoning about devices in the home. And hunches always start today with a voice interaction. So you saw one of the hunches was triggered by Jay setting an alarm for the next morning. It looked like Jay was going to bed. So this was a trigger for Alexa to go and kind of double check all the devices in the house. Just see if everything looks right. He's going to bed, so let's just check on his behalf and see if there's any hunches. And there's other voice signals that will lead to a hunch. For example, I think in the morning we used a turn off. Jay said turn off a lamp, and then that triggered Alexa to double check the house and just see if everything looked right. So we start with that voice interaction. Goes through the models to check for anomalies and sort of kind of filter through to what seems to be high confidence anomalies, something that she might deliver a hunch on. If she has a hunch, then she delivers it as a response to that voice experience. So you heard Alexa saying, by the way, I noticed that your lock is unlocked. Do you want me to lock it? That's the way a hunch manifests. So for hunches, there's a few different pieces. So the first concept we have to develop is that of activity prediction. And activity prediction relies on several pieces of data, very similar to did you mean in terms of the base. So we're looking at all these different types of data, voice interactions, device state, what time is it, things like that. And the idea with activity prediction is really we're trying to predict how likely is the customer to interact with Alexa right now. So whether they're going to have a voice interaction with Alexa, are they likely to navigate to a light in the app and turn the light on or off, something like that. And this is useful in a couple ways for hunches. First, it's useful as kind of a proxy to whether or not the customer is kind of present in the home and engaged with their smart home, as opposed to maybe away on vacation or away from home, because we can then use that data for conditioning on the training data, right? So if we can split the model to represent patterns in state when the customer is home versus when they're away. It's a very different behavior in the home. So activity prediction is one of those concepts. And then the notion of activity is part of this next really core concept in hunches, which is that of state prediction. We're trying to predict what the state of each device probably will be based on everything Alexa knows about it. And so let's look at that. So there's both a global and a local component to the state prediction. And the first sort of global component is a deep neural network which takes several inputs. So one is this input which we call device common name. So the idea about common name is that customers name their devices all kinds of things, right? You may have a light that's called my bedside lamp. I might have one that's called Evan's favorite lamp. Someone else might just have one that's called lamp, but they're all lamps, okay? So the device common name for all these devices would just be lamp. So there's kind of a mapping between, all these many variations on names to like a certain type of device, certain canonical name for a device. And so the implicit assumption that this model is based on is that devices with certain names tend to behave in a certain way. And in addition to that, of course, this model leverages patterns in device state, the activity prediction we just talked about, as well as the time of day and light level outside, that kind of thing. And then this produces a prediction of state. And then just as kind of an example for why this global prediction is particularly useful, why it's useful to look across all customers to try to predict the behavior of a device having a certain type of name. So in this visualization, it's an animation. I'll play it in a second. On the left-hand side, you'll see a typical winter day in the US. And then on the right-hand side, you see Christmas Day in the US. And within each state, we have aggregated the proportion of lights that are on in that state at a given time. And then it's too small to read, but there's little numbers in the state that are representing the proportion of lights that are on. The color is more important. Now you can see right now all of the states are blue, indicating that most of the lights are off. And then when we play the animation, some of the states will light up more orange, indicating that a higher proportion of lights are on. So on the left-hand side, again, is the typical winter day, and then on the right-hand side is Christmas Day. Let's see if we can get this to play. Okay. So you can see on Christmas Day, everybody's up much earlier in the US, and the lights stay on most of the day. They even stay on a little bit later in the day. And so, of course, there's obvious intuition here, right? So for people who are celebrating the Christmas holiday, they're probably getting up early. Maybe they have some family around, and it's just sort of like an all-day affair, and so the lights are on all day. However, from the perspective of a model, there's no reason to value December 25th as more important or distinctive or heavily weighted than any other day, right? So for a model trained on an individual's data, it would take years to figure out that something happens on December 25th. We gotta watch that. But if you have a global model, you can find out very quickly. You can see December 25th once, and then you can see for a big cross section of homes, this is kind of a special event, and we want to be able to learn that quickly. So a global model helps us do that kind of modeling as well, accounting for special events, holidays, sporting events. The Super Bowl is another one. Okay, so. That's the animation. Okay, so then there's another component. I said there was a global component. There's a more local component, which is a graphical model. So this is more of a probabilistic graphical model that represents relationships among devices in the home. And this kind of toy example that we have over to the right is showing us that for a kind of a bedroom light at home, say it's an overhead light, the probability that that light is going to be on is determined not only by the past behavior of that light, but by the sort of state of other lights in the house, such as the reading lamp, as well as the time of day. For example, the global model is also an input to this graphical model. So we have information about what a typical bedroom light would do at this time of day and in these conditions. That's an influence on the prediction for state for this given bedroom light. And then a little more on the reading lamp, which appears on the left side. So if the reading lamp is also in the bedroom, maybe it tends to be the last thing on before bed. And if the reading lamp is on, it may signify that all the other lights are off in the room. So that may also determine the state of the bedroom light. So it's just a refinement of state based on everything we know about the house right now. So given state prediction, given a refined prediction of state, leveraging activity in the global and the local model, we then detect anomalies. And so there's many algorithms for detecting anomalies. And essentially the intuition here is just that we have a prediction, we have sort of Alexa's intuition about what the state of the house should be, and then we have the actual state of the house, and when there's a difference and when it's sort of significant enough, we can flag that as an anomaly. The important thing to note about anomaly detection in this part of Hunches, in this part of the flow, is that it's all statistical. It's a statistical anomaly detection. So it's correct statistically. This lock is usually not locked this time, or the fan is usually not on at this time. She's correct about that. But it does not necessarily mean the customer did not intend for the lock to be unlocked. There are cases where customers do things that are statistically anomalous, and it's totally on purpose. So there's one more piece to Hunches that's important to look at, and that is a prediction of the customer's intention. Right? So we can detect anomalies fairly well, but we also have to see whether or not this is an anomaly that looks like it was intentional or an accident. And so we have a model that does that as well. And so let's take a quick look at why this is important. We have a visualization on the right here. This is a kind of an old plot on some noisy data, even prior to working on Hunches. It's kind of an initial experiment, but it kind of illustrates the point. So using utterances only in the summer of 2017, in August, we found that there were patterns of anomalies. So this is showing an aggregate count of all device anomalies in the US in August of 2017, and it's on kind of a day-by-day basis. So, across the x-axis, we see a few peaks here over day by day, and then the peaks here correspond to weekends. So, unsurprisingly, devices tend to be on later on weekends. And then, interestingly, there's also this spike which occurred on August 26th of 2017, which was kind of almost a global anomaly. And it wasn't one of these situations like a holiday like Christmas Day. It was something different. I wonder if anybody recalls something happening on August 26th, 2017. Dad's birthday? That was a big event. I was celebrating that also. It wasn't a birthday. It was a sporting event, but it wasn't something like the Super Bowl, which was regular. Olympics? No, it wasn't the Olympics. It was across the street. It was in Las Vegas. No, sporting event. Mayweather, that's right. It was the Mayweather versus McGregor boxing match. So at that time, the Mayweather versus McGregor fight was on, and it was this super produced event. It had something like 50 million viewers in the US. And so this big spike corresponds to living room lights, televisions, and kitchen lights all being on at the same time. Right? So this was all anomalous, statistically speaking, but it was totally intentional. So Alexa is able, with this intention model, to kind of capture some of the reasoning about what intentional and unintentional anomalies look like. But this is the kind of thing that is very useful to model, to represent, because otherwise you get into the business of explicitly modeling every kind of possible holiday or sporting event that may be localized to any particular city, so on. So this part of the model really helps filter hunches to those that are truly about accidental state settings rather than intentional. So we deliver the hunch if Alexa decides that this anomaly is unintentional, and then the customer gives feedback to the hunch. So in the example from the demo, Dylan said yes to the hunch about the door, and it locked the door. He said yes to the hunch about the fan being turned off, and Alexa turned off the fan. And so that's another piece of core feedback that we use to iterate on hunches, to refine our sense of what is intentional and what is unintentional in the state of the home. And so hunches by nature are about anomalies, so they happen much less often than DYMs, but when they do happen, customers tell us that they are really a delightful feature. So some people feel like Alexa has really helped them, makes them feel like Alexa's watching out for them and getting smarter over time. It also, of course, when you get into things like lock hunches or hunches about sort of maybe safety-related scenarios like a fireplace being turned on, they feel like hunches are also a way to help keep them safe. Okay, so the last product that we're going to talk about is Alexa Guard, and this is one that is definitely a focus on safety. And the part of Alexa Guard we're going to talk about is away lighting. And as Dylan showed in that video, away lighting is really about making it look like you're at home when you're actually away from home. So the end-to-end look at away lighting starts with the customer's request to initiate away lighting. They say that they're going to leave home, and we need to figure out how to turn their lights on and off in a realistic way. And there's an important requirement for away lighting that's worth mentioning, and that is that Alexa has to come up with this plan for turning on and off lights kind of from day one. Like if you just buy lights and screw them in, install them in your smart home, you should be able to use away lighting immediately. You should be able to walk out of your house and Alexa will do something intelligent with the lights in your house. So there's no prior knowledge of anything going on in the house that you could use to start away lighting. And of course, Alexa gets smarter over time. Away lighting gets smarter over time, but it has to work on day one. So it starts with this customer request, and the goal is to use what Alexa knows about the customer, again in this day one scenario, to generate a schedule for turning the lights on and off in the home to mimic actual realistic behavior. So there's a few models that we use here. And the first is a model for state prediction, again. So there's a similarity to hunches in this sense. And then this model is again more of a global model. So the data we use are kind of in the same general categories. We use the device registry. Particularly important are the names of the devices that the customer provided. Those are data that we actually have on day one. And then in the sense of a global model, we have this data on state changes across all customers. So we can use that to develop our sense of what looks normal for a home when it's occupied, what devices are on at a certain time and what devices are off, how long are they on, how long are they off. And then again, we're always including this additional kind of situational context about what time is it light out, is it dark out? It's unusual perhaps to turn on lights in the middle of the day, but we consider the time of day and the light level as well when making this prediction. So the global state prediction, to kind of dig into that, we again can consider the pattern of a device as being represented by a curve like this. And in practice, this is actually represented using a deep neural network. We feed in all these signals, and we again use the concept of a common device name. So if you have something that's called, Bob's lamp, it gets regularized to lamp, and then we use the prediction for what lamps typically look like. And what we can see in this example to the right is that devices named front porch light. So this is the type of light that we saw before in the Hunches example. It's actually for devices named front porch light or similar. And so what you see in this pattern is that kind of after dark in the middle of the night and then early in the evening when the sun sets, front porch lights tend to be on, and during the middle of the day, front porch lights tend to be off, and that is a similar pattern across many front porch lights. So if you've got a front porch light, it's likely that a way lighting will suggest the front porch light is probably going to be on most of the night. Okay, another example is the living room light. So for living room lights, it's a different pattern, right? So starting, and again, the x-axis starts at midnight and goes to the midnight of the next day. So looking in the evening, living room lights have a high probability of being on during this kind of prime time between, like 7 and 10 p.m. into the evening when people are sort of gathered at home with their family or watching TV. Living room lights tend to follow this pattern. And then there's a little bump in the beginning of the day, maybe in the morning, but it's less common for living room lights to be on at that time. So away mode is going to lean towards turning living room lights or devices that are somehow named or flagged as being in the living room, turning those devices on during that sort of prime time. And then just another example, sort of important family of lights that we have for away mode are bedroom lights. And these follow yet another sort of common pattern. They're mostly on in the evening, just before bedtime, and they're on typically for a little bit shorter duration than you would see of lights like living room lights, because people don't really spend as much time in the bedroom. And then again, this one has got a little bump in the morning as well. Maybe when people are waking up, they turn the bedroom light on, but it doesn't last that long, and it's less likely. So for this global state prediction for away lighting, we use those predictions about whether a particular type of light is going to be on or whether it's going to be off to help inform the choice of whether we're going to turn that light on or off. We also use the duration, the typical duration or the distribution of durations for that type of light. So another one we didn't show are bathroom lights. People have bathroom lights, and typically those are on for the shortest amount of time, right? A bathroom light might be on for a few minutes, whereas the living room light might indeed be on for several hours. So we take the predictions of the duration, we take the predictions of the likely state for these devices based on their names, based on the data in the device registry. And then we send that through to some business logic that's really doing the planning of the schedule. And so this kind of works out so that all the durations and the predictions of a light being on or off look natural across the home. And then there's also some business rules about keeping lights on, even if the selection of lights you have they may actually be all off if it was looking totally normal, but because away lighting is really trying to deter anyone who might be looking at your house, there's business rules around, okay, well, we must keep a certain number of lights on, that sort of thing. So the business logic is applied to the predictions, and then the schedule is produced, and then that's used to control the lighting in your house while you're away. And then also worth noting that this happens on a recurring basis. So you can turn on away lighting and you can be out for a week or days at a time. This will happen as often as it needs to schedule realistic lighting. And that said, a few notes about the Alexa Guard and away lighting feature. This was announced last year, and it had been in limited release until May 14th. It was made generally available, so if you have Alexa and smart home, this is a feature that you can use. You just have to have named lights. And it's very early, but we're already seeing how this feature is improving the safety of customers' homes, helping them keep their homes safe. So overall, a few closing remarks, kind of looking back at these themes. We've looked at several products. We've looked at the Did You Mean product, which is sort of a core initial product aimed at using machine learning to make the smart home simpler to use for customers. We looked at Alexa Hunches, which is trying to understand customer behavior and respond to it more proactively in a way to make smart home more convenient. So, remembering things that you might have forgotten or doing things on behalf of the customer is really what Hunches is about. And then we also looked at the Alexa Guard feature, which is clearly about safety. So for those more security-driven smart home customers, one of those new customer segments. And we also showed that, especially with respect to the Did You Mean feature, but also true about Hunches and Alexa Guard, we are able to combine spoken language understanding with additional data from the devices. So additional data concerning behavioral patterns, data concerning the sensed context, what time of day it is, the light level, and so on, current state of devices. All of these are kind of brought to bear in the machine learning that's used to power these smart home experiences. And with that, again, the goal is really to make smart homes simpler, more convenient, help customers stay safe. And looking forward, there's really, of course, a continued investment in all these areas. We're going to use machine learning to keep making the smart home simpler. We're going to make it more convenient for customers by being, responsive to the right things at the right times. And we're going to keep working to help customers keep their homes and their properties and families safe. But in addition, there's kind of several emergent themes that we can talk about. So one of them is kind of a shift in interaction with the smart home. So everything today is really oriented around the device, kind of like classic smart home. So I want to turn on the light. I'm really talking about that one light, that one device, and I'm thinking about the devices involved. And we're going to see a shift towards tasks rather than specific devices. So orientation of Alexa around what the customer is doing, what their activity is right now. And smart home should be supportive and responsive to that. Secondly, of course, we're going to continue to scale internationally, which includes scaling to other languages. Also, scaling to other cultures is really an important thing for smart home because there's many differences in the way people behave in different countries, right? So for those of you who may be from the UK, as an example, the way people use heating in the home in the UK is very different from the way they use it in the US. So that's something that also has to be represented in the models, and there can be maybe some knowledge transfer, but generally there's more research to do to support different areas. And then lastly, we need to understand more about who's home and at what time. So if we can know who's in the house at what time and what their sort of personal patterns are, we can know more about how to support that particular customer or how to support a family of customers in a way that's reliable and consistent for that family. So that's kind of a high-level review of some of the features we've worked on in the last year. As we said, we'll continue working on them, and we're excited to share more of this with you at the next Remars.